So with that, we have concluded everything that we need to talk about for a z-test. So now it's time to move on to our next hypothesis test, the single sample t-test. Now what's great about the single sample t-test is that it's pretty much identical to a z-test except for one major principle or one major concept. And so the single sample t-test is going to feel like a review except for this one change, which we'll talk about today. And the reason why I want to talk about today, and I want to get to this particular aspect of the single sample t-test, is because you're going to conduct a single sample t-test in lab on Monday, and then when we come on Tuesday, we'll go through the hypothesis test from start to finish for a single sample t-test. So let's get the basic concepts out of the way. That way when we come in on Monday and Tuesday, we can just get right down to work and do our hypothesis test. And you'll find that the test the second time around is going to go a lot faster because, again, it's very similar to a z-test. So before we really begin, we needed to define what's the difference between a z-test and a t-test. And so here on this slide, you'll see that the assumptions for a z-test are that the dependent variable is scale, that participants are randomly selected, and that the population is normally distributed. Finally, there is an assumption that we have the parameters for one of the populations. So in other words, we have the mean and the standard deviation for one of the populations. The difference between a single sample t-test and a z-test is that last assumption. It's the parameters for one of the populations. So in a z-test, you have both the mean and the standard deviation. But with a t-test, all you have available to you is the population mean. So note that that population mean may be given, or you may need to calculate it. So if you can calculate the population mean, then you have the population mean. Sometimes I have students who are given a set of data and they don't think they're given the population mean because it's just not given to them saying the population mean is X. They don't realize that they can calculate that population mean, and that's the same thing as being given the population mean. So whether we're giving it to it outright or you have to calculate it, if all we have is a population mean, we don't have a standard deviation, then we need to conduct a single sample t-test. So again, we're comparing a single sample, one sample, to the overall population, but now all we have is a population mean. We don't have a standard deviation. We actually see this a lot in practice when it comes to census data. Census data is great for giving us means, but they never include standard deviations. And so we have a population average to compare to, but we have no measure of variability. So with a t-test, what we're going to do is we're going to estimate that standard deviation based on the sample. So remember, when we sample, we want to infer back to the population. So if we get a standard deviation for a sample, then we can infer that back to the population. However, there is a formula problem with the formula that you've learned so far for a standard deviation. So before we can do a t-test, we need to correct for that problem in the formula that we've learned thus far. And so we need to make adjustment to our standard deviation formula. Okay, so the particular problem is that our measure of variability, so in this case sigma for the population, is on a theoretical normal distribution. Now this theoretical normal distribution is an infinite distribution. So if you remember, when we have the normal distribution, it never touches the x-axis. So that x-axis ranges from negative infinity all the way to infinity, and that's at a theoretical level. So in theory, it never touches that x-axis, and so it continues for infinity. However, the sample variability is not infinite. It is finite. There is a low number in our sample, there is a high number in our sample, and we can't get below or higher than those numbers. And so there's cutoffs. It's constrained, whereas the distribution in the population, the theoretical distribution, is infinite. So the best way to illustrate this is to look at the range. And so the range is a measure of variability. So in a population, as we just mentioned, the range goes from negative infinity all the way to infinity. And so the range is infinite in the population. So here we have a normal distribution. Again, as I was mentioning before, you see that the distribution does not touch the x-axis. It asymptotes on that x-axis. It gets closer and closer and closer, but it never ever touches it. And so the range on that x-axis goes from negative infinity all the way to positive infinity. It never ends. However, for a sample, that range is finite. So if I was to put a sample distribution and overlay it with my population distribution, I would see that the sample distribution will touch the x-axis because we account for every single value in the sample. And so maybe I have a sample, just for an example, I have a sample that has a low score of 4 and a high score of 25, and all the remaining scores or values are someplace in between. And notice that they're more frequent towards the center and less frequent towards the tails. But you can see that the sample is constrained between the two values of 4 and 25, where they touch the x-axis. There's no values below 4 and there's no values above 25. And so when we compare that to the overall population distribution that is infinite, that doesn't touch that x-axis, we find that the measure of variability, in this case the range, is less than the population measure of variability, or the population range. Population range is infinite, the sample range is finite. So if we want our sample to better represent the population, then we need to increase the variability. In other words, we need to increase the range of our distribution. Now remember, there's several measures of variability. In fact, there's 3 we've talked about. We've talked about range, we talked about variance, and we talked about standard deviation. But it's easier to demonstrate it with range, and so that's what we're talking about here. But regardless of the measure of variability, we need to increase that variability so that it better represents the population distribution. So again, the population distribution in this case, the range is the population variability. The range is infinite, and in the sample's case, it is finite. And so we need to increase, or we need to change our finite sample distribution, turn it into an infinite population distribution so that we get a better representation when we infer from the sample to the population. So here's our measure for standard deviation. So again, standard deviation is a measure of variability, and it's on our theoretical normal distribution. And again, this distribution is infinite. And so this is the formula that we're used to, and so you'll notice that in the denominator we're dividing by, in this case, the population size, or n, the number of observations in our population. And so this is for an infinite distribution. So again, the problem is that our sample is finite. It has a finite variability, and so we need to somehow increase that variability. And so here is our formula for estimating a population standard deviation from a sample. So you'll notice that our symbol is no longer sigma, it is now S. So S is a Latin Roman letter. It signifies that we are using a sample to estimate the population standard deviation. And so if you look at the formula, it's pretty much the same as the standard deviation formula for the population, except for one difference. We're now dividing by a different number. So instead of dividing by the population size, or n, the number of values in the population, we're now going to divide by n minus 1, or the number of observations in our sample minus 1. So we're going to subtract 1 from the number of observations in our calculations. And when we do that, we turn a finite distribution based on our sample into an infinite distribution that's estimated to the population. So always remember that the sample variability is always less than the population variability. And so if I want to estimate from my sample and infer back to that population, then I need to increase the variability. And I'm going to do that by subtracting 1 from n, or from the number of observations in my sample. So we call n minus 1 the degrees of freedom. The degrees of freedom is the number of scores that are free to vary when estimating a population from a sample. So in a sample, we have a set of numbers. Well, those numbers can either be free to vary or not free to vary. So why is it in our formula that we subtract 1? And what does it mean to be free to vary? I think the best way to demonstrate this is to use a problem or an example. So let's say that we have a sample of 3 values. So our n equals 3. And let's say the mean of these 3 values is 5. So what are the values of the 3 numbers? We know there's 3 of them. We know the average is 5. So what is the value of our 3 numbers? So if you said that there are multiple combinations that would meet our criteria of our problem, so in other words, multiple combinations of numbers that would give us a mean of 5 with 3 values, then you would be correct. In fact, there are an infinite number of solutions. So just as long as those 3 numbers average out to be 5, we can have an infinite number of values that could represent our particular problem when we have a sample of 3 that has an average of 5. So for example, our 3 numbers could be 6, 5, and 4. The average of those 3 numbers is 5, and so that meets the criteria of our problem. But also, the numbers -20, 7, and 28 would also meet that criteria. The average of those 3 numbers is also 5. We could also use the numbers of 1,212, -100, and -1,097, and that would still meet our criteria. The average of those 3 numbers is again 5. And so there's an infinite number of solutions to this particular problem. Just as long as the average is 5, we can have any 3 numbers that exist. And so there's no shortage of solutions. So let's adjust the problem just a little bit. So we'll still say we have 3 numbers, and we'll still say the average is 5, except now we're going to put one of those numbers in there. So let's say, instead of having 3 question marks, let's say that one of those numbers is 6. So then what are the values of the last 2 numbers in this sample? Again, if you said that there are multiple solutions, then you would be correct. In this case, there is still an infinite number of solutions that would solve this particular problem. And again, just as long as the average of these 3 numbers is still 5, then we would meet the criteria for our problem. So for example, if we had the numbers 7 and 2, then 6, 7, and 2 would still give us a mean of 5. Also, if we had 1,000,009 and -1,000,000, we would still meet the criteria, because 6, 1,000,009, and -1,000,000 would still equal an average of 5. And so again, there's still an infinite number of solutions that meet this particular criteria. So let's adjust our problem just a little bit more. And so again, we'll still use our sample size of 3, and we'll still have our mean of 5, except now let's give 2 of the numbers. And so in this case, instead of just having a 6, we'll also uncover another number. We'll say it's 5. And so I have 6 and I have 5, and then I have this question mark. So what is the value of that last number, or that 3rd number? Well, if you said the answer is 4, then you would be correct. And so the next question would be, could that last number be anything else? Could it be anything else other than 4? If you said no, then you would be correct again. It can only be 4. It can't be any other number but 4, because we have to meet the criteria of the average equaling 5. And so for the average to equal 5, then our 3 numbers must add up to 15. So 15 divided by 3 is 5. And so if I know that I have a 6 and a 5, in order to get 15, I have to have a 4. And it can't be any other number. So in other words, that last number is not free to vary. It is a finite number. It is not an infinite number. And so that's where we get our degrees of freedom. And that's why we subtract 1. We don't subtract 2, we don't subtract 0.5, we don't subtract 1.5. The reason why we subtract 1 is because for any particular sample or any given data set that we get an average for, every observation in that sample is free to vary infinitely except for one of those values. So if I have a sample of 5 and I know 4 of those numbers, then I know what that last number is going to be. It can't be anything else. It's a finite number. So if my number of observations in my sample is 5, then 4 numbers are free to vary infinitely, and 1 number is finite. It is not free to vary. If my sample size is 10, then I have 9 numbers that are free to vary infinitely, and only 1 number that is not free to vary, that very last number. And so when we talk about degrees of freedom, the reason why we subtract 1 is because we're trying to remove that finite number. So theoretically, if I remove that finite number, then I am left with just infinite numbers. And so in my sample, if my numbers in my sample can be anything, if they're infinite, they vary infinitely, then my distribution by necessity must be infinite also. All values in my sample would be possible, and that would create an infinite distribution. So, our degrees of freedom tells us that in every sample there is one finite value. The rest of the values are infinite values. They can vary infinitely. So if I want to convert a finite distribution to an infinite distribution, I have to remove that one finite value from the sample. Now this is theoretical, of course. We can't really do it in practice, but theoretically, if I subtract 1 from my number of observations in the sample, and that one number is the finite number, then I'm left with just infinite numbers. And so my distribution will now be infinite because all values are possible within my sample. So once we remove that one finite number, the remaining values are free to vary, which is our definition of degrees of freedom. So the degrees of freedom is the number of scores that are free to vary when estimating a population from a sample. So in other words, in any sample there is one finite number, one number that is not free to vary. We're going to remove that number from the data set, at least theoretically. And so we'll subtract that one number out and we're left with just infinite numbers, or numbers that are free to vary infinitely. So because we're using a t-test, because we're estimating the population distribution from the sample distribution, then we can't use our z-distribution anymore. And so now we have to use what's called a t-distribution. So our t-distribution goes with our t-tests. The z-distribution goes with our z-tests, or with z-scores. And so I won't go over the t-distribution here in this lecture, but on Tuesday we will go to that table and we will practice with it and make sure that we can get critical values based on the t-distribution that is in your book. And so just as a reminder, here's the formula that we're going to use. This is essentially the only difference between a z-test and a single sample t-test, is the fact that we're estimating the standard deviation in the population. And to estimate that standard deviation, we are going to subtract 1 from the number of observations in our sample. And again, when we do that, we change our finite sample distribution into an estimate of an infinite population distribution. And of course now we'll use the symbol S for standard deviation rather than the Greek letter sigma.